Good morning. Well, this morning we have Dr. Mark Demming with us. He earned a bachelor's degree in chemistry in 1986 from California State University at Los Angeles and a PhD in chemistry in 1992 from the University of Southern California, where he researched on the mechanisms of carbon-hydrogen activation on osmium phosphate molecules. It sounds very brainy. Very fascinating, I'm sure. He has taught chemistry at Pasadena Community College. When moving to the Northwest, he spent most of his time teaching chemistry and mathematics at Portland Community College. He is presently retired. He has presented lectures at DSA in the past on the Human Genome Project and engineering marvels of cholesterol. He's been married for 42 years and has 2 grown children. Let's welcome Dr. Mark Demming.
Well, hello. I'm Dr. Mark Demming, the original, I think. Though at times my name gets spelled with 2 M's because if you're saying swim and then swimming, you always add 2 M's, and that's the way it always goes. But it's only 1 M in Mark Demming. Well, we're going to be talking about this wonderful thing called sugar. And just before I get my presentation, I want you to realize what to kind of expect and not expect. I'll even tell you some of the things expect and not expect later on. But one of the things is going to be a lot of math, but it's more of accounting math, and it's not going to be the same kind of math you normally hear when you're hearing about biological stuff. So I'm going to take you in a different route than you have. On the other hand, some of the conclusions you get are going to be very much the same. But since there was math and there was sugar, I thought, you know what? When I first started thinking about this, I started thinking, how can I get myself into the mode of this? So I started presenting myself a math problem on it. I said, well, let's see. How many cups of coffee would it take to eat 8 cinnamon rolls? And I tried those things, and you know what? It didn't work out that well. So I tried to get myself in the mode of this. But now we're going to be talking about this thing called sugar. So with that, first of all, this will be, unfortunately for you guys, will be my only scripture, but really the scripture says a lot. Especially verse 10 specifically talks about honey, but it says, the law of the Lord is perfect, refreshing the soul. The statutes of the Lord are trustworthy, making wise the simple. The precepts of the Lord are right, giving joy to the heart, and the commands of the Lord are radiant, giving light to the eyes. The fear of the Lord is pure, enduring forever. The decrees of the Lord are firm, and all of them are righteous. They are more precious than gold, than much pure gold. They are sweeter than honey, than the honeycomb. By them thy servant is warned, and keeping them is great reward. One of the things it mentions here is about laws, and about wanting to obey the laws of, let's say, a creator. If the creator is there, which I believe there is, and I believe this creator talks to us, but these laws, we find laws out there, and we want to know something about these laws, and which laws can we say are, in fact, what I'm going to be talking about is natural. So, and specifically, the question I want to ask, and hopefully get to answer by the end, is nature natural? Sounds weird. But what I mean specifically is biological nature natural? So I want to know, is all this biology stuff, is this something that occurs naturally or could occur naturally? And I'm going to make my point using sugars because I really like sugars. And so, but at the end, I kind of hope to get the conclusion that, by using sugars, I'll show that biological nature is not natural. Which sounds strange because we almost base our word on natural on biology. Because biology happens everywhere. You practically can't take a step with finding some biological thing, a grass, a weed, a bug, all over the place. So, wow, it must be natural, isn't it? Okay, so, but why sugars? Well, first of all, biological nature is built up of 4 major building blocks. You guys probably even know them. Maybe there's 5, maybe there's 10, I don't know. But I'm going to pick 4 because I think those are the 4 biggies. We're going to have sugars, which are the sweeter things, or the things we're going to talk, and carbohydrates in general. We're going to talk, there's amino acids, there's fats, and there's nucleic acids. With those four, that's a big bulk of the biomass, and then you can add a lot of other little stuff like ions and metals and this and that, and we have a lot of those in our too. But so I can do this talk actually using any one of those subjects, and I can do pretty much the same talk, and I'll end up with the same conclusion. I'm just going to happen to use sugars. Okay, and one thing about any one of these is you can't talk about any one without bringing up the other three. They just are best buddies. They hang together. They just are tighter than, I'm not sure what they'd be tighter than, but anyway, they're tight. One package deal, as I put up there. And also, I like sugar. So I thought when I decided to do this talk, let's do it on sugar. So I know this is kind of small, but what this talk is not, I'm not going to try to convince you in this that God exists. This is not a talk about trying to convince you God exists. This is also not a talk where I'm going to introduce some wild concepts and new concepts that you've never heard before. Almost everything I do you can find on the internet. In fact, I use the internet for most of it because it's hard to find and collect information in any one source that wanted to talk about the things I want to talk about. So I had to go there, and therefore this is all available out there. I'm just going to take it from a view that you may not have seen it from this perspective. What it is I'll talk to about India. I will try to simplify some biochemical concepts, but you know what? There's no way to do that because, my gosh, there's so many names and so many little things that go on. In fact, I'm not going to even focus on to the little things that go on that much. I'm going to stay away from that. And that's the part, that maybe get people messed up on. So I want to do the big pictures. And then I had two bullet points there that I've left blank. I'm wondering, was it because that's so super secret and I can't let you know about that? Or is it because I put a couple in there and just forgot that I was supposed to put something and then I go, no, I don't really want to have that, and I've got to take the bullet point out. Anyway, so there's nothing new, nothing breaking through, everything you can find out there. And now a lot of times it seems so easy. In fact, oh my gosh, I've gone to site after site after site of these people that make these great animations, and they actually do this thing called storytelling. That if you want to memorize something, you can't just give cold facts. You have to put it into a story and make it this. And this is easy. And so you talk about chemicals, that this chemical wants to do this, and this enzyme wants to do this, and I have a desire to this, and I don't want to do that. And we put this emotions and everything else and make a story out of it to make it easier. And so there are things that can be diagrammed, and there are certain things, like I'll be talking about, let's say, many of the processes where I'll go a string of reactions, where the fact is it may have 8 little molecules that then it goes through, and the thing is, the thing that makes this interesting, the thing that makes this so cool, the thing that makes this incredible as we go through that, is there are only 8 little molecules, and not 10 that you might get if you just put these things together without the enzyme. And then with each one of those, you'd have to isolate the thing you want, and then you'd have to and that's the way researchers do that, as you may not know, is they go, we found this little tiny sugar out there in the wild on an asteroid, and guess what? This sugar could make something. So what we're going to take is we're going to take pure sugar, a bucket load of it, mix it with this and say, see, it reacts. It wasn't that sugar, and there's not enough of that sugar to do much of a reaction at all. But they purify it and then do reactions on it. But the reality is almost every reaction I'm going to be talking about can have actually multiple things it can do if it was in the wild without biological constraint. So, I know the results of each step. That is amazing, which makes these things a lot easier to do. Now, why are there actually so much on the internet for showing how this is easy? It has to do with something called money. It ends up that a lot of people want to take the MCAT exams for medical school. And when they do that, they said, you know what? I need to memorize all these things. Can you make it easier for me? And they're paying money to somebody so they can make it easier for them. And so there's money out there. So there's a lot of really cool animations, not driven by desire to have knowledge. There's money to be made there, folks. Okay, so if you're seeing stuff out there, the reason there's a lot out there, there's money to be made in it. Now, the enzymes are really big. That's actually the very big thing I'm going to talk about is the enzymes. And I'm going to focus on, you'll see a lot of my talk is focusing on enzymes are really big. Can you tell me something about enzymes right now from just the information I've given you? Real enzymes are big. Oh my gosh, you guys are a great audience. At least one is. Now, now the thing about enzymes, there's a lot of other things about them that also we have to kind of keep in mind in this whole thing is they're specifically shaped. They're regulated by specific chemicals. They're created under instructions from DNA, RNA. In fact, there's not an enzyme that exists in this world, biological enzyme, that isn't created by DNA, RNA. It doesn't exist. It always is, it's always made from this. Sometimes there's only one target molecule. Sometimes there's two things that have to be brought together to have things happen. Sometimes you have to have a thing over here to add energy so it changes it so it can go ka-chunk and makes this one over here. So it's all these little places and all these little things all around that thing that have to work. And so they're not just, there's no enzyme out there that is really all that simple. In fact, I'm going to show you lots of pictures of them. We won't worry about memorizing pictures. I'm not going to actually diagram the picture. I'm just going to show you the pictures saying, you know what, there's a lot of stuff out there. So the focus of this talk is really going to be how big and how much does it cost, right? That's the thing. If I want to make, this particular device, I'd say, well, how big is it? Well, this one's not that big. But the question not isn't how big is this? How big is the factory that makes this? And how much did it cost to make that factory to finally get 10 million of these things that are made? So how big is it? That's not this. It's the factory. So I'm not focusing on little molecules. I'm focusing on a factory, the enzyme. And I want to know how much does it cost? Okay, so that's a big deal on this thing because I want to know. And we're going to kind of look at what we're going to be doing. So I'm going to talk about, first I talk about what is natural and natural, a little bit about what is sugar, and where do I find it, maybe how sugar is unmade. That's actually the big part of the talk is how sugar is unmade. How do you take sugar and break it down? And then I may have a little tiny two-slide thing on how do you make it, but basically it's a reverse of how you unmake it. So anyway, and then we're going to do our break, and then I'm going to try to pull it all together and say, what is it that, what can we tell from the information right here? What does that tell us? And what can we get out of this? So what is nature? Well, usually it means it comes easy. Like, she is a natural, throwing the ball and such. I was not the natural one when it came to physical things like throwing balls. My brother had all the sports genes. I didn't get them. I would go out and play basketball, and he'd be running around me, flip over, get the basket in, shoot, basket. I'd be going, sitting in one place, shoot, basket. So anyway, that's me, no sports genes. But we also mean natural that it's found in nature, like, we also mean that it's the physical stuff. There is a natural part that is physical, that has to do with weather. That is like water evaporates, and then water condenses as it gets colder up in the air, forms bigger particles, then falls down, and then do all these cycles. We can talk about certain chemical reactions or things that are just chemical to chemical without doing any special thing to it. How do those react together? So those would be kind of physical stuff. There's biological stuff like plants, and that's also called nature. So I'm going to be focusing on the biological stuff like plants and animals. Now I'm going to focus on nature as not natural, and I'm going to first kind of break up kind of laws in my own view, and not that there aren't any other ways of breaking up all of our world, but there are physical laws out there. That's going to be the laws of things that are going to be where bonds are made, or that you have ion-ion attractions. You can have electrical interactions of a moving charge creates fields and all those other kind of things. So you can have quantum forces where you can take two positive things that should want to fly apart and squish them together, and somehow they stay together. That's called the nucleus, with some neutrons in there, and that's the strong nuclear force. So anyway, we have all these little forces that we can look at and have nothing to do with life, have nothing to do with living, has to also do with all the particles and how they work together and interactions together in our universe. Then, which includes a lot of things, but there are physical laws that have nothing to do with anything in biology. In fact, all of biology has to obey those physical laws. There's nothing in biology that ever violates those laws. There's no miracles in biology, though sometimes you think there is. Then there's going to be, now it's kind of strange. This is strange. I have to introduce this because people don't talk about this. But there are information laws in our universe. And you're going, what? Sounds like a philosophy class now. There are. You know that there is information out there. We know that if you have a book, there's information in it. Now, one of the things about information is I have that last thing on one of the laws about it is information is not only as meaningful if it's interpreted. And that's what we're trying to do is sometimes we're trying to look at all the bips and blops and signals that come from outer space and see, is there some information out there that I can interpret and say there's intelligence out there? Is there any information out there besides randomness? And so may look for it. But that's one of the things information is completely independent of any physical laws. For example, I can say, I like donuts, the words. I can have it inscribed on metal. It doesn't take any more energy than have it to put it on a screen or to have it just located in my head. Or put it on a thumb drive. There's no difference in the material amount, no different change in matter, except when you inscribe it, you may have to move some metal atoms around. But the idea is that there's nothing about that. The information is the same no matter where I put it, store it, see it, use it, whatever. The information is the same. It doesn't change by any physical laws around it. I can put it in different places. The thing is, too, information can be destroyed, whereas material in the universe, the way that we think the universe works, is that the amount of matter plus energy is constant in our universe. At least is the way that we have shown it, at least in our local corner of the universe, is that in the experiments we've done, you really can't create or destroy, we should say matter, but there has to be a matter-energy combo. Because sometimes matter can be turned into energy into matter, But basically, it can't be created or destroyed. What we had is what we have today and tomorrow. Information can be destroyed. If I take a piece of information, I love donuts, and I destroy everything that has that, any audio, video, everything that has it, finally get it all gone, that information is actually destroyed. I can destroy information. And information can be created. It's a question of how do you create information? That's a tricky thing. Because that's many times, for as most as we know, information is created by people that have, some sort of intelligence. But the thing is that there is this thing called information. Whether you like it or not, it's out there. DNA is one of those pieces that has information. How did it get there? I don't know. I mean, actually, it's one of the things that we'll see. So if we have physical laws are natural, informational laws seem to follow also kind of, these are things that it can do and can't do. And again, those are not connected at all. Then we come to this biological laws. And what is biology? If I had to distill all of biology into one thing, and some people are going to maybe yell at me and say, there's no way, that doesn't even say it at all. But the idea is that based on an internal input, almost all structures in any biological thing you find are formed, modified, implemented by performing tasks involving mechanical or chemical reactions and properties that allow the organism to exist and replicate. So it's one of the things that organisms need to do. They need to exist. You need to have the stuff there. You need to replicate, make more of them, and they need to be able to create all little stuff in it. And so that they do that, and the internal input is that information that's there. Now that's been a big question for a long time, is how does it get there? Some people say, well, maybe the physical world has that information that can be imprinted on it somehow because of physical laws and physical this. We've not shown that. We're not come close to showing that. But let's say that's a sticky point with how do we get that. Okay, let's talk about some sugars. And this is the stuff that I know you're going to dislike. There's a lot of sugars out there. Okay, these are ones up here that have. These are all the kind of sugars you can make. We have some up there that are 3 carbon sugars, 4 carbon sugars, 5 carbon sugars, 6 carbon sugars. There are 7 carbon sugars. I'm not going to show them. The idea is that all of those have a D in front of it. Is that because they're delightful? No, that's not what the D is for. It just says that if I was to go to the bottom, right there, I was to go 1 carbon up, Every one of these things is going to have that OH on that side. Every single one of them, that from the bottom, the second carbon up, that has that OH, it's going to be that. Now, this is called a Fisher projection. What it is, if you were to look at there, everything on the two outsides right there, you see those things hanging out like this? All of those are supposed to be going towards you, which means the carbons are going backwards. So it's like kind of bending backwards to one another. So that's how it goes. And so that if you were to take this and turn to the side, form into a ring, the way that they usually present it as these ones are usually shown down, and these ones are shown up. Okay, so so on this side, it's on the right. You know, I missed one day in kindergarten when they taught right and left, and my whole life has been messed up. Okay, so on the right-hand side is going to be the down and the right. So when we show these, we're going to show them in a ring form because that's the way in nature it mostly forms. And so each one of these is a D because of that one. And there's actually 3 other sugars there, and also it has a C double bond O and an OH, 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 OH. So to be a sugar, it's got to have one C double bond O. If it's at the end, it's called an aldehyde. If it's in the middle, it's called a ketone. If it's not any other oxygens attached to it. So anyway, so on the ones, and again, the reason I'm taking isolating those 4 is those are kind of the 4 biggie, at least for human, what humans use. Though actually, you can find almost every single one of those. Most of those you can find in humans. You can find some of them, and also all of them you can find in plants somewhere. But those are the biggies. I want you to notice their names that you may have known. In fact, this is one of the ones I love so much, ribose. It's the one you find everywhere, and we're going to see ribose again and again. And so I'm team ribose. I love that sugar. Okay, now, then we have the one that you know heard a lot about is glucose. That's sometimes called blood sugar. Then there's mannose, and then there's galactose, and that's sometimes called milk sugar. It's going to be found more in that kind of group. But it's so you can find these kind of sugars that are going to be used together to make combinations of things. And those are going to be the ones. Now, if I was to now go ahead and look at the ones where I have where I had that double bond O at the end, at the top part up there, I now move it 1 carbon down. And I move it 1 carbon down. I move it 1 carbon down. This is a kind of ketone, so we call these ketoses. I should mention now, ose ending means it's a sugar. And a ket is just a general kind that has, versus a specific kind, that has this double bond one. Now you're saying, if you get over here, can I put the double bond down below here? You go, yeah, but it really is not. It's not really important. Or if it's important, it's only for a short intermediate to do something. But no, so you don't normally do that. The biggie one here is going to be this one, fructose. Now, ribulose and xylose are also important. In fact, if you were to go out into the Northwest and look at all those trees out there, you're going to find a lot of this xylose in forming something called hemiacetals. And this xylose, which we'll talk about later on, actually doesn't want to exist. This xylose wants to will form a 5-membered ring. This fructose will also form a 5-membered ring, and it doesn't really want to. And we'll talk about fructose a little bit. It doesn't want to find, when it does form it, it doesn't want to form it. Okay, so how many sugars did you guys remember from those slides? How many did I circle? 4 from the first and 1 from the second. So basically, we got the ones that we're going to look at is like 5 of them. Now, sometimes you show this other projection here, which I love the way the chemists do this. They form it in this nice, it's as if it's a flat hexagon because it makes such a pretty picture. So we'll call all these diagrams are what we call cartoons. It really isn't how far spaced away carbon is from hydrogen, spacing-wise. No. It's but you space things really far apart, show these lines between so you can see the connections, do things, cross lines. But what this does, the middle one, you don't care about. What I do care about is that whenever I do take a sugar, where I'm going to take this H over here, OH over here, and I'm going to put this H over way up to here, and I'm going to form a ring on this glucose. So typically, whenever I'm forming a ring, where I'm going to form it from this OH. Can it form from that one? Absolutely. Do you find it in nature? Not really. That if I use this one and I form a ring like this, it forms this 99% of the time. If it uses this one here, it forms it 1% of the time. In physical nature, not in biology. Biology doesn't really use that one. But anyway, here's the key on this one to know. Whenever these things got these OHs and this C double bond O, there is a reaction you can do in chemistry that makes it so they can hook it together. But normally, if you just took a C double bond O and you take an OH and you try to do it, it doesn't work that well. Because it's in proximity, it's always wiggling around and bam, and wiggling around and bam. And it forms this kind of ring structure. One of the things it can do is it can form the OH down and form OH up. Now, this is important for us is because once it forms this and you react this down, called the alpha form, it's something we can break down and we can use. If it ends up forming the OH, if it does this form where it forms the OH up, and both these are equally energetic pretty much, it can form, it is something that we can't break down. Because once you attach something to this oxygen here, it's fixed in that ring. And that ring is actually kind of a chair form, but anyway, we'll not worry about that. So, okay, we're trying to get something about sugars. So I got a few sugars here. One of these is glucose, which is a 6-carbon sugar. We have galactose, which is a 6-carbon sugar. Therefore, it's called you could have a zillion names for all these things. In general, anything that's got 6 is called a hex. Anything that's a sugar is an ose. So both those are going to be hexoses. So you get all these names and you go, what's the specific one and what's the general one? Anyway, that's confusing. I won't worry about that. Don't worry, we're not going to worry about it too much. I want you to, one of the things to note is this is also a 6-carbon one, but it forms a 5-membered ring. Can this one form a 6-membered ring? Yes, but it doesn't get this little thing I call the flag. Nature loves the flag, because that flag, you can hooky things to it. And if you hooky things to that flag in this fructose, you can only have a 5-membered ring. 5-membered rings, it doesn't like. It wants to be in the 6. It actually feels more comfortable. But if it's in a 5, it's like, ugh. But it's forced to. This poor guy, fructose is always forced in this one. And now even though this can open and close, they almost always show it in this way. Even if it can do all that, because that is really the way it's going to form when something happens to it. And so they keep it in the something's going to happen to you phase. And that's what this is right here. These OHs on this end can be reacted on. These right here are usually hooky places for things like phosphates and other things. Like this one has 2 places I can hooky things like phosphates. Now phosphates you can hook on any place you want to. And that's the thing in nature, in physical nature, I try to just put phosphates in general on something. I'm going to connect it to everything. In biologic nature, I'm only going to probably hook it up to here, up here, or if I have 2 of them, I'll maybe hook one there. And then in the last one is ribose. Team ribose. I'm team ribose. Team ribose, 5-carbon sugar. It can exist in the 6-membered form. In nature, ribose is only in the 5, because in the 5-membered form, and making a ring of 5 members with an oxygen. Oh my gosh, I went backwards. No. I can get there. I can get back. I have technology. Okay. If it's in the 5-membered ring, it has I call it the flag. The carbon sticking up, I can do things with. And remember, in biology, it's all about doing things. And guess what? It always forces it to do what it doesn't necessarily want to do. If this was to, so it's just one of those things that we get it so things can happen. So that's what you're going to see a lot of in these sugars. You'll see these sugars where you have the flag, something's attached to it, and you'll have something attached on this end, and every once in a while this little OH here. Now glucose has an OH up, OH down, OH up, OH down. This one, galactose, has an OH up, OH down, so it's different in this one place. And that makes it so if it has a place it has to sit, this will sit differently because it's got different OHs where it's attached with some maybe hydrogen bonding. The one thing to mention about these two guys in ribose is you have the two oxygens here for regular ribose, like you make RNA with. Ooh. It's got two legs down so it can hook with two little spots for hydrogen bonding if it needs to fit on something. Two legs, fits spots. It's like tacky, little Velcros. And that's how it's used many times. You'll see occasionally it's missing this H, and that's called D, because there's no O there, but everything else is the same. They call it deoxyribose. This one you can, they actually find these on asteroids. Tiny amounts, you can find them. This one you don't. So would it be found in physical nature? At least when we see asteroids, nope. but it's everything. This right here is what makes your DNA. Do you guys have any DNA in you? I wonder if any of you do. Anyway, you probably have a lot of it, at least, a couple billion base pairs of those things. So in your DNA. So anyway, sometimes it forces things to be things that wouldn't in the natural world be. Or you'd have to take a lot of work to get them there. Okay, so we're going to go some of the things, don't worry, we'll go faster as we go through. And we're going to build up speed, and then you're going to go, what? Okay, so this is just to say that, yes, my favorite, fructose, can be a six-membered ring if it uses the outside oxygen, but it wants to use that outside oxygen there as a hooky place. So it actually exists in not the six-membered ring, which is favorable in the outside world, to a five-membered ring, which is a little more unfavorable. But you know what? I got a hooky spot. And so then nature forces it to be that way so it can use it. And then I won't get it. Even ribose can be in a six-membered form. It's usually done in a five-membered form. No, there is actually a five-membered sugar called xylose that makes this thing called hemiastose that itself would rather be in the six-membered form. It's actually in the six-membered form because it doesn't need the hooky, and so it can do that and then hook out. So anyway, and that makes up a big biomass of those trees you have out there. In fact, the harder the wood is, the more xylose you have in the wood to make it stiffer, to make the hemiastols in there. Anyway, so that's kind of point. Okay, so now we're going to go on. We're going to now go quicker. Disaccharides, a saccharide basically is a sugar unit. Now, all the things we're going to talk about are built up of sugar units. Everything in biology many times is built up, this piece and this piece come together. And then you may have to modify it a little bit afterwards, but you have these pieces that are parts. In fact, that's what you get from nutrition. That's what you get from your food. You're going to eat your food and grind it up, and you're going to break it up into parts. The parts come into you, and then it gets put together in different ways, and boom, you have you. Now, so parts are parts, and this is the lowest part of anything called a saccharide or a carbohydrate is a sugar unit. And so sugar units can be, did I hit something already? Okay, I went there. Okay, so these are three disaccharides. I can take a glucose with the glucose, and we're going to call that maltose. And I want you to notice, I'm going to mention this a lot. I'll keep on mentioning this. See this on this side of it? Because I always draw it this side. Flag on this side, up. And on this side, I have the O going down. That's called an alpha. Alpha linkages. I get an enzyme to break that. Poof! This is usable sugar. I love it. Now, this one down here is going to be called lactose. Ooh, the O's going up. I don't have an enzyme for that one. That don't break that one. So can I use this one? No. Now, actually, it's a yes and no. If you're a little baby, you actually make the enzyme that breaks that because mommy's milk has that in it. And you have an enzyme when you're younger, and then as you get older, that enzyme starts dissipating. And then but then you're also having bacteria in your stomach that also is breaking it down. So most of the time, it's the bacteria in your stomach, that's the lactobacillus and such, that will break it down for you. But otherwise, you can't break this down, and it just goes right straight through you, because you can't break that bond yourself. You have to have somebody else help you. So you got a lot of helpers inside there helping you. Not all bacteria are bad. Okay, and then in this one over here is something called sucrose. You've heard about it, table sugar. And one thing to note, the O is going which way? Down? I can break that. I can break this in two parts and use it. And this is the parts I have now are going to be a sucrose and a fructose. And then those can be go on to use and go to different places. Okay, so we got a disaccharide. You can get a trisaccharide or more. There's anything from 3 to once you we're going to start chaining these things up. Once you start chaining, you can go from like 3 to around 9. They call them oligo, which means kind of like there's some. And then later on we'll get to poly, which means there's a lot. So this happens to be I'm going to ask you some questions on this one real quickly. It's 3 sugars, so it's a triose. So this one happens to be called raffinose. This has got it's hard to see, but that O is going up. Can I break that one? No. It's also connected to the hooky part, which also means usually it's a branching thing. I can't use that. But this one's going down. Ooh, can I break that one? Yes. So that means I can actually break off this fructose and use it. This right here just goes right through me. I can't use it at all. So I can only get the parts where I have the enzyme to undo the parts the right way. Same thing with this one. This is called stachyose. It is also, this has a little bit of sweetness because it only has one of these ends here. Usually the more things you attach to it, the less sweet it gets. But this can be sweet in your mouth because you can break it apart. This one, it's got a bond coming down. I could actually break that one off, and I can use that one. But this one over here is a flag, and actually we can't break flag bonds. So it can sometimes break things if it's just another sugar, but it's the flag part, not the regular part. So actually the flag one, we can't break it. This flag one, we can't break it. This one, we can't, but we can break this one. So out of all these 4, the only one that we can actually use for nutrition is the last one. Everything else goes straight through you. Now some bacteria can use it, but we can't. Anyway, so now we're going to go quickly. Polysaccharides can be from 10 to 1,000 to 10,000, so we can have a lot of them. Depends on which ones. Amylose is connected by the oxygen going down. And now this is where these cartoonish things get weird. Normally, wherever you have a bend, it's a carbon, but in these cartoonish connections of sugars, that bend is not, it's just basically, I'm just trying to make it nice and easy and everything apart. So instead of doing 2 lines of sugar like this, but it ends up that amylose, it makes it look like, does that look like it's in a straight line? Amylose, the way it hooks, it actually it folds like this and kind of wraps around. And it tends to form kind of loops because it doesn't naturally want to go straight. Because it actually hooks at an angle. So it goes this one, hooks to this one, hooks to this one, hooks to this one, and it many times will form these chains that then fill up with water. And this would be, one of the carbohydrates you get from eating carbohydrates. This one is amylopectin. Now it has a lot of carbons struck together, but it has one branch. So it goes straight, and then it's got a branch. And then it goes straight, then it has 2 things going straight, then it's got maybe 2 branches. And so now you have 4 of them going straight, and then another one. If you're talking about wheats and stuff like that, it goes like every 20 to 30 carbons specific to, the number is actually specific to the particular plant. It'll go 20 to 30 carbons, branch, 20, 30 carbons, branch. Now, the little baby cotyledons that are going to use this, they actually have the enzymes that break this one like we do, going down, but they also have an enzyme to break that, so they can get a lot of use out of this. If we were to eat this, all we eat is from the ends until we get to a branch, stop, and then the rest of it is not usable, goes down through us until the bacteria breaks it up for us more. Okay, so we have those. How long can these amylose be? Amylose, if you're talking about potatoes, more amylose than amylopectin. Amylopectin is the one with the branches. That's the one you find in in wheat, and that wheat is going to have more amylopectin than amylose. Because of those branches, it allows it to kind of keep its structure, and you can form bubbles around it, and that way you get bread with bubbles in it. That's why you use wheat for that. Things that don't. Now, this is what amylopectin would really look like. It starts off with 1, and then it branches, and then 20 more, then branches, then 20 more, then branches. And so really, all that we can do, because we can only eat it until we get to a branch, we can only take the stuff at the end, but once it gets to a branch, we stop. And we have to let the bacteria say, okay, it's all the rest is yours. We got the low-hanging fruit. You get the harder stuff, and that's all we can eat. And so you can have a granule, like it looks messy like this. Now, actually, remember I told you these things don't really want to be straight. They're actually curly cute. So it's all over the place. And now this is called glycogen. This is the way we store sugar if we need to store it. We could make this long chain of sugar and then say, okay, I want you to get sugar from this one end. But it's slow. I have to wait for this one enzyme to go through it because I can't do anything else. Usually what it does, it breaks it up, and then it breaks it up, and then it breaks it up, and every 6 to 8 carbons, breaks it up, and then it gets some long strings out the end, and that's what you eat inside your cell. You do have a debranching enzyme in your cell, not in your stomach. But it will actually just eat those things at the end until it gets to a branch and stop. And what happens if you have muscles and need more because you're working out a lot? Well, you actually create more of these guys, which have more branches, which you can work on more at once, so you get more sugar at once, and bam, it's about mass producing sugar into you. And so, but that's your body's way of doing that. It just makes a lot of branches and the ends. Okay, easy to eat stuff, and then you can release those really easily. Okay. Now, there's cellulose, which can be 7,000 units to 15,000 strings long. Is 15,000 a lot? Yeah. Okay, and so that one's going to go, so we're going to have those. We have chitin, which also polysugars, which make the if chitin is hooked together kind of loosely, it makes the bee's stomach and the flexible bee parts. Or if it's hooked really hard, it can make these hard shells like the outside of a beetle or the crustaceans. It depends on, and the hemiacellose is 50 to 300. It's actually the one that when you make cellulose, you make it in these cellulose. I'll show it down here. You make it in, that's the second one down. Don't worry about the top one. The cellulose one is you make these strings, and actually these ones are straight because it's done the beta. It actually makes it straight. Then you put 1, 2, 3, 4 together to make a bundle, and then you put a couple bundles, and that still is pretty flexible. Then you put some bundles with bundles, and then that's where you get the hemiacids and lignin and other things that go between. The more stuff you have between that stiffens it up, it can't bend as much like in woody stalks. If you have a lot less, now you can bend the leaf without breaking the parts of the leaf. If you get to this where there's more of those, that gets harder to do and it breaks. So you can see even in leaves from the center part, it breaks easier than if you get the leaf, you can fold it more. So it means that they have fewer things with fewer things wrapping around it, connecting it, making it tight, making it huge ropey bundles. So that is, and there's cellulose actually it's the one thing in this world, this planet, that the greatest biomass of sugar is cellulose, made from trees and plants and such. Animals don't really make it, but it's the stuff that's left over, and it's the stuff that's left over when all the easy parts are taken out by all the bacteria. Cellulose is the hardest stuff, so you're left with the hard stuff to work with, like the hemiacetose, the hemicellulose, or the chitin. All those things are left around because they're the harder ones to break for everybody. Anyway, and then there's chitin, I talked about that. Now, here's the thing to notice about chitin. It has a place to make a special hooky thing that goes out from it, and allows it to make a lot of cross connections, which is why chitin can be so tough and hard. And you have to take those crab things, because the chitin can cross connect a lot and put other pieces in there, whereas sugar doesn't do it. Okay, other places you can find sugars because we're just getting sugars, and then we're going to get to the actual talk I was going to talk about, is that you can have, like in a cell, you have this, oh my gosh, we have to mention lipids again, cell walls. So you can have things that are basically markers on cells that tell your cell who you are you the right one, should I get rid of you? And so we have, and that's where you get that, like for us, there's those blood types, A, B, and I put the ABO, I put the ones over here. You have this lipid unit, this lipid thing over here sticks right down into here, so it holds it in there. Why it's flagging this thing around. Hello, this is who I am. I'm a sugar group of this kind. So you have the base one, sometimes called H, sometimes called O. In this case they use an O, but sometimes they use H here. It's the base one. It has a glucose, a galactose, a modified glucose, and a galactose, and then a fructose. Whew, a lot of different kinds. It needs the kinds to say, I'm special, okay? And then that's an O, which means you have the thing without any extra things on it. And if you're a B, you have just a plain, you add an extra galactose at the end there, boop. And if you're going to be that's a B type, I'm sorry, if you have an A type, you do a modified galactose. A galactose or a modified galactose, you know what? Your body can tell the difference. If you're A, you only have A's on there, on the outside of the cell. If you're B's, you only have B's on the outside of the cell. If you're AB, you got a mixture. You don't know what you want to be, but you got two of them. So you got, and then if you're an O, all you have is just the beginning string thing that's not ready yet. It's going, I got late to the party. Nobody put anything on me. You know, and so you may have ones that just have those and nothing else. And your body can tell the difference, and it sometimes rejects one versus the other. Or if these things over here, now these, there's not as many glucoses in this one, but your RH factor, that's the plus and minus on AB plus, AB minus, A, whatever. That's the glycoprotein that's got some things on it that then your body can say it distinguishes it itself. But you do have other what we call glycoproteins, and I think I did one, I just list a whole bunch of glycoproteins where you mix and match things. So you can mix a glucose with a lipid, a glucose with the protein. Some glucoses mixed with proteins are used for the immune system, are used for hormones, are used for blood plasma proteins, are used for structural proteins like collagen, are used for created like mucus. Sometimes those are glucose and protein mixed together. So where can you find glucose? Just about everywhere in the body, out of the body, and sometimes if you spit, it's not even in you anymore. So watch out for that. So maybe you can appreciate spit now with that. Okay, so now this is the big part. Now this right here is where it's a lot of accounting. I'm actually doing a lot of number crunching. I'm going to add things up. If you're going to sleep, this is the part to sleep, because it is going to be like, oh my gosh, well, another one of those numbers and another one. Okay, that's okay. So that's why I even put the B's there are sleeping. I'm going to look at glycolysis, which means you take table sugar and you break it down to a 6-carbon sugar to a 3-carbon sugar. Then we're going to move that into, and actually I'll put that as part of the citric acid cycle, we're going to have to move that into a special place called the mitochondria to do some energy stuff. And it uses those 3 carbon. The first thing it does is it's going to strip off a carbon to make it a 2-carbon. That 2-carbon is going to go on to a 4-carbon, which then does a bunch of stuff, loses a carbon dioxide, gains a lot of stuff and goes on. But anyway, a lot of stuff happens, and you have the electron transport system. Now, all of these together are what's going to, at the end, make something called, what's the energy unit that every part of the body needs when it needs energy to make things happen that won't happen by themselves? Calories are is the energy unit, but the coin that the body uses is ATP. Now, it can use something so closely related to a GTP, which can be changed in ATP, but it's the coin. If you need something and it needs to put up in energy, you need some ATP to help you get there. You can use some other things for it, but that's the energy coin that's used everywhere. If you want to run a cell, any cell that's living, every cell that's living, from bacteria, the lowest bacteria, is there low ones? Senator, we think that. The ones by the sulfur springs, maybe they, because it's stinky, they're the low ones. And all the even high-falutin bacteria, E. coli. Or maybe you can find some or plants and animals. Everything uses ATP. That means if there was a time that things came from a common ancestor, supposedly around anywhere from 2.5 to 3.5 billion years ago, long time ago, and we all diverged from that one little thing, it figured out, I want to use ATP as an energy source. And there's lots of things that will also be common to every single thing. Like every single organism that exists out there has DNA. And it uses the exact same 4 bases in DNA. And the coding for the proteins is pretty much the same on all organisms, so the code information still works. So anyway, they use the same proteins, no matter where you are, whether you're the lowly one in the sulfur springs, or whether you're the upper, you still make the same molecules. You still have to do this, it still has the same coding, everything's the same. So if we branched, it had to be billion years ago when, and then we're going to talk about, well, could we have even then created something to make something happen even then? So we'll get there as we crunch the numbers. We're going to focus on the machines, the enzymes. So I want you to just kind of understand now what's going to happen overall in all this process is you first have to add energy to get a little bit higher energy, and then as you start doing things to that glucose, you're going to start grabbing energy out of it, and so you can make your ATPs. So what's the goal? Make ATPs. Okay, so that's the goal, is make ATPs, because you need to feed the ATPs to all the other parts of the cells that are making things. If you want to make a cell wall, you need ATP, because you need to make all the lipids. And, and people, they talk about all the time, and this is not a fat talk, but I just want to mention this. They talk about, you can find lipids out in nature all the time, yes. But can you find phospholipids that are anywhere from 14 to 18? To make the cell wall just the right width. So it's not too thick, not too thin, and to find them with the phosphorus on there with some other things and have these lipids from 14 to 18. How many of those you find in nature? Actually, you don't find any. But let's not worry about it. But you can find fatty stuff everywhere. You can find it, if you're on planets, asteroids, you can find not the kind you need or in the quantity you need to make the thing you need, so everything has to make it itself. Now, you can't steal it from somebody else, like we do steal lipids from other plants. So, yes, okay, I will say we don't always do it ourselves, so we're not. But somebody somewhere made that lipid. It didn't come from some sort of physical natural source. Every lipid that we use comes from a biological natural source. Okay, and then you're going to release a couple things. I just want to mention these guys because they're used a lot. So we're going to have, this process right here, in terms of just breaking it down, it gives a couple, makes 2, gives 4, because once you're here, you've actually broke this into 3s, and now so you're making 4 here, and every one of these after this is a 2 and a 2 and a 2 and a 2 and a 2. So you're going to start to get some things coming down here, these NADHs. The NADH is an electron grabber, grabs pairs of electrons. And electrons, they're dangerous. So whenever it grabs a pair of electrons, it's like I got to take it somewhere. I got to put it somewhere. I got this pair of electrons. And it's going to move it somewhere where it can use it to make energy. But these are high energy electrons. Every one of these guys stole some electrons, 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 yes, and then stole some electrons. And it's going to use those electrons to make a boatload of ATP. That's the goal, remember? In this whole thing is, how can I take that original glucose and make a boatload of energy so I can feed all the other things that need to go on, which don't happen unless you make this. So my goal is, let me look at all the factories that make all these different components going all the way down. And so, in general, this is what you have. You have don't you love chemistry things? You're going, do I count the number right? I have this thing called glucose, but it's actually, this represents any 6-carbon sugar, but this is supposed to be specifically glucose without showing any structure. And some oxygen. And you guys know if you take glucose and like polyglucose, which is like tree stuff, and you put it in with oxygen, and you finally get the initial spark to get it going, what happens to it? Kaboom! Fire is going everywhere, and so you get a lot of energy out of that. Well, it's got to capture the energy in such a way that when it starts somehow adding the oxygens in there, it's not going to burn you up. Well, guess what? It never lets the oxygen get close. Okay. What it does is it has a whole process of the glucolysis citric acid cycle, whatever, is creating all those little pieces that are going to go on somewhere else and a few ATPs. It actually uses oxygen and water to burn it. Who would have thought? Burning up glucose with water? Hello? Yet that's an enzyme that allows you to do that. And then it grabs oxygens and grabs these electrons, 12 electrons through the process, 12 pairs of electrons, and then it gives off some protons, so you're getting kind of more of an acidy environment, and you want those. We're going to use those protons, don't worry. And then we're going to after doing all of that, we're going to take those two electrons and protons. We're going to bring them over to a whole different over here, away from the other guys. We're going to do a whole different process, and that's going to be called the electron transport process. And it's got to keep it separate. And what we do is we take those oxygens and we just kind of shove some electrons on them. Boom, 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 boom. Because they love to receive electrons. Oh my gosh. They're one of the best electron receivers. So if you're going to drive this whole thing and we're going to talk about all these electrons that have to go from here to here to here to here to here, like 13 to 15 spots. They got to jump from here to 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 here. Finally end up in oxygen because it's a big sink and it loves electrons. If you had to use something else like sulfate to be an electron grabber, you have to actually you can only use fewer things and you don't get as much energy out. But if you use oxygen, oh my gosh, you get the most bang for your buck, which is why most organisms use oxygen for doing what they do. Anyway, you can, if you're in a sulfur spring, you don't have any oxygen, yes, you can use other things, and they do. Anyway, and when you do this electron transport, when you put these electrons in there, and it uses those electrons going from higher energy to lower energy and driven all the way down in the process to pump a bunch of protons up on this pump, a pump inside a cell, hello, and it pumps them up in a couple different ways, one by directly pumping it up, one by passing hydrogen here, passing hydrogen here up. Another pump, I love that, it's mixed all in this. But eventually, you're going to push 112 H's up the stream and to the other side of this boundary. And actually, the way that the mitochondria is built up, it's got an outer cell and an inner cell and an outer membrane, inner membranes. And inside the inner membranes, you're going to have to pump these electrons in between there, and they're going to use that to drive this thing over here, to drive a third thing, which is an ATP pump, which is driven by all those protons that are up there that are put up at high potential, and it's going down and it's going to drive a mechanical thing, which then puts out a lot of ATP. I'm producing somewhere between 28 and 37 ATP. Is that because I'm just not good at math? No, it's just because actually scientists aren't good at math either, because they really don't know. Is it every 4 ATP that comes out? That for every four hydrogen things that come down, you get 1 ATP, or is it every 3 hydrogens that come down, or is it a mix of both? And sometimes some of those hydrogens actually go up and leak out, and so it doesn't. So anyway, on average, is what people will say in practice. They figure it's about 28 ATP out of this cycle, give or take, allowing things to kind of go bad every once in a while in practice is what they guess. It's, these things are so tiny, trying to measure how many ATP coming out of you. It's difficult. It's difficult work. Anyway, so what does it do? It has three big systems, all interconnected. So at the end, you get the energy coin, ding, 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 that comes out the lottery thing that you can then feed into things to make them happen. Okay, let's go through. Now, we're going to go through this fast because I need to keep them going. So this right here is just basically, it's a lot of information I don't care about. What I do care about is that there's an enzyme there, between every step there's an enzyme. So I'm going to look at all those enzymes, and I'm going to start counting the cost of that enzyme. The only reason I mentioned GAP here, is because that's kind of intermediate product come from plants. When they make carbon, they make GAP. And that GAP can then go back up to make glucose, or it can go down to make pyruvate. So a GAP is really, it's that glycerol aldehyde phosphate. Anyway, so I just mentioned it there is just because I want to. But I want to look at all the how much cost does it make to make all of those factories before you can get one glucose through? How much does it cost to even the partway point? Okay, first of all, I'm going to go through each enzyme and say how many amino acids are in it. For example, the first enzyme actually is a dimer. Each one has 450 enzymes. It's called a homodimer. It really is two identical ones that do the same action hooked together. Whenever you see two things hooked together, it means these things have to be controlled. It means one more way to control it. It adds a new control point by putting it together, as opposed to being apart. So it allows more control by hooking them together. It allows more control, things that can control it. But basically, I'm going to count this, even though this whole thing right here is two of them. This right here is another view of it where it's showing this side is one of them, this side is the other. I'm going to count it as if I'm going to count only the one side for my count. So it comes as a twofer. I'm counting just the one. And that's 450 amino acids. Okay, that's not so bad, 450. I like it. Now all those amino acids you had to attach, boom, kaboom. Every attachment costs somewhere between 2 to 4 ATP. I'm going to make it easy. I'll go with the low number, 2. So I'm going to multiply. You'll see me every time I talked about how many amino acids. It's going to cost to make it in my machine that's going to make it. It's going to cost twice that. So 900 ATP is what it's going to cost. Remember, I'm trying to get out ATP, not use it. But I got to make the factory that makes it. Okay, so how many have I got? 450 so far. Okay, we'll start counting these things up fast. Number 2, this one has 300 in it. Ends up as also as a dimer, but each one's 300. I'll count 300. 300 amino acids for a single one gives me 600 ATP that's going on. I'm going to do a lot of math and counting here. You guys, somebody's going to write these things down for me. I hope I can remember them. This one, sometimes they also give these things in weight, kilodaltons, before they actually know the structure. And the trouble with this weight here is this weight may include waters, it may include a lot of other things, so you can't always figure out how many residues are in it with that. But then I had to go look around, and I found that it's a tetramer. Each one has 765 amino acids. And now maybe I can mention some of the things. You can see some things look like these ribbons that are curling. That has to be formed that way. Because normally you just form in a straight structure. It's got to make them so they form these little curls here. And this little curly group here. Now when it does a curly group like that, what it does is the amino acids are sticking out of it. Boom, 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 boom. It's kind of like a tree trunk, flowers coming off of it. And that's the ends that have the special abilities being water-loving, water-hating, being charged, not charged. Those are things that are going to be on the things. Now, sometimes you'll show some things on there that are flatter pieces, like right down here. Because in that case, instead of wrapping around, it tends to go like this, flat. Because it needs it to be flat in that area. In this area, it needs it for structural things and for it being connected to the water. Now, if this thing is hanging out in water, what you'll find, if you really look at it, is that all the ones that are facing out towards where the water is are always going to be water-loving residues. Which means I can replace it with another water. If I did a mutation and that was the one and replaced it with another water-loving residue, it wouldn't affect that thing at all, pretty much. Unless it's right at the active site. Then you got to keep it, it's got to be exactly the right one. So that's why they'll say, oh, this section of it is conserved. That's because that's where the action's happening, and that one can't change. Otherwise, if it changes, it doesn't work. If this glucosyl thing doesn't work, you die. And there are genes that have things changed, and where things like that, and the living organism never exists, never comes out. Because if you can't get out the coins to make everything run, it's not going to run. So some places you can't change, and we say those are miraculously conserved. It's because you can't change them, or you can't have life coming out of it. Anyway, there's a lot of other places you can change the things out as long as it's water loving. Now, if you have 20 water loving, and then also you can change one to a fat loving in water, well, that's probably not going to change it that much, even though it really doesn't want to be that place. It's okay. And then some of the residues will internally come in, and they'll overlap and connect, and that's why it keeps its shape. But there are folder proteins that I'm not counting that actually cause that to be in that shape. So I'm not even counting the cost of those. Okay, 360 is in that for the single one, even though it's in a group that does it in a set of 4. This one goes in a set of 2, and each one is 250. I don't even care what it's doing now. I'm even ignoring the name. The name usually says, what do I start with? And that's usually how they name it. I think it started with this thing, and I think this is what it does, So, and almost all enzymes will end in ASE. So, what I do, ACE. who I'm working on, ACE. That's the name of it. So if I work on, so this one must be working on a triosaphosphate isomer. So, this is just changing. Where the phosphate's over here, it's moving it over to here. Okay, it's an isomerase. It's going to basically change where things are, move some things around inside. Okay, anyway. But what it does is this one's only 250. Boy, I see someone's 400, 250 doesn't seem like a big one, as it were, because now I'm getting jaded. I'm seeing some 400s in there. Woof. Okay, so, and then I get to number 6, and I see it's got a complicated shape. It's got a lot of curly cues. It's got some flatty areas, and sometimes the researchers will say, you know what, I got this one dialed down. That it happens right here. I don't know where it actually happens in this one. And sometimes they go, well, I think it kind of happens here-ish. And they take a big, we're not sure exactly, because what happens is to get this structure here, many times they get them by making crystals of it. It's shaped like this. But when you put it in a thing where things are going to crystallize, it may go, and then you're thinking, well, that's the way it is in nature. Actually, it's like this. And so then they have to backtrack and say, well, it's like that, but that doesn't work. We can obviously tell. Let's see if we keep on making pictures of it and making models of it and see if we can get it to that. And then you have to make some guesses. And we're going to talk about some places on these that always have the same, so no matter how it's put together, it'll have a certain kind of shape. It's always there on it somewhere. We're going to talk about that. We're not there yet. 7, okay, that's 415. That's on the higher side of the ones. I've seen a 450. This is 415. This is number 8. It's only 250 amino acids. It's a dimer, but we'll count only one of them. So I'm just counting this here. Number 9 is 430, okay, the higher end. And now I put this alpha, beta, gammas because it actually has, in some of these, it may have, for doing this one, it may have 3 completely different genes making the same one that's slightly different. But any one of these, and this is an important part, any one of these, you can take them and you can actually have here's the gene code that has the gene, and it's got these things called introns in it. So, and it knows to take out the introns, and what it does with some of the ways it uses those introns is that you have the base piece, but it can have this one if you're in the muscle, or it can use this one here if you're in if you need the environment to be a little bit different to be in the, nerve cell, or this one would be in the liver cell, and so it can have some variations within one protein. But sometimes the variations are big enough to be in one region versus another. It'll actually have separate genes to do it. And that's why there's the alpha, the beta, the gamma, but you know what? They all make this basic thing. And so that's the cool thing about some of these things, and the body knows how to do that. I'll talk about something else of where do you find these on the DNA a little bit later. Okay, here is pyruvic kinase. It's going to basically take off a phosphate. It's 500. I think this is my topper so far. 500, number 10. Woo! Okay, so now we got them. This is not my spreadsheet thing. If I did the individual sets and I add up all the amino acids, I have 3,605. That's a lot of them. You got to make them. You got to find them. You got to build them. to make just one of these. And that means you need, at the total at the end, you need 7,210 ATP you need to make it. Woo, I'm going to have to go overtime to to make up for that loss right there. And then if I add all 10 sets, I won't do this every time. This right here, remember I had 10 sets, but if I do it the actual as doubles or foursomes or whatever, I end up having almost 10,000 amino acids to make it the way it's actually going to be, in humans at least. And then that's about 20,000 ATP I had to spend that I've got to make up before I can get even one out the door. Okay, and that's just that first part of it. Oh my God, what's going to happen? Yes, you are my God, and I think I know what's going to happen. Something, anyway. Now here's a word from our sponsors. I've been sponsored by the nucleic acids. They said, you have a problem. That's our motto. We have a plan for it. And from planning to implementation, from supplies to supply chains, we'll take care of it. We are the nucleic acids. Coding, information. Okay, anyway. So now that I got this, now I'm going to go through another little thing called pyruvate processing, which means you end up at pyruvate at the end of that one, and you got to then bring it, where am I going? Then you got to bring it over and basically take a CoA. What's a CoA? We'll get to that later. You take a CoA and you take this 3-carbon thing, you stick it on, you remove one of the carbons as carbon dioxide, and then you're going to bring it out with a few other things in there. Now, this CoA has a sulfide bond, so you have to put a sulfur connected to it, to that group. Here's what we get out of this. Okay, I'm not even going to show you. I'm going to show you the enzyme second. But I'm going to give you the numbers first. You actually need to take that pyruvate and move it carefully into the mitochondria. It's got a carrier. So you have to make the carrier before you can bring it in there. So I'm going to count those. Not very much. 109 units, 127 units. Not very costly, but you need it. Okay. Then the dehydrogenase has 3 parts and a connector thingy. Can I call it that? And that's the binding one. So, but the first part actually has 2 parts to the first part that are very different, but it needs to have those put. So now this is the first time we're getting a complex where you need 2 different parts to make something that works. And then it has a separate one, which is there's the E, which has the alpha beta. There's a E2 and E3, E1, E2, E3. And so here's now again, to make one of each one of those things, I need 2,642. That's a lot of stuff going on in there. Now, what does that look like? It looks like this. It forms very complex things, of which this is just one version of it. This would be in humans. This would be in in yeast. But the idea is the same. You have the E1 as a former, tetramer. So it's 4 of the same things hooked together, which means whenever things hook together, you have more control. Also, you have this, where am I going? You have this E3, and here's my E2 down here, and my E3. I kind of separate because it's hard to see that. In fact, in some of the things, it took me a lot of going through the internet to figure out which ones were which. Now, let me tell you something about this guy. This guy ends up being, if you take the E1 tends to act as a heteromer, has comes as 4's group. The E2 comes as a onesie, and the E3, even though it shows the E2 there with a 4, it really kind of comes more onesie, and the E3 comes as a twosie. Okay, but if you were to count them up, what it wants to do is it gets these bundles of them, this whole bundle, massive bundle, and this is one of the few places you can see that, you know what, this isn't always so simple. It does a bundle of 48 tetramers to 48 monomers of the E2 to 12 of the E3, so essentially you get an overall ratio of 8 E1s to 2 E2s to 1 E3, and so you end up, if we were to actually take that, it says you have individually, you have 192 and a 48 and a 24. That's a lot of bundles of these things. And they're all hooked together by these little hooky pieces, which we're showing right here. That's the hooky piece, that allows it to do things like, I put this here, I move this here, move this over here, I move this here to do this, I move this here to do that. Ba-boom, da-boom, ba-boom, ba-boom, this little hooky thing can move. And so it does all these things in there. Anyway, so, and so you get this essential, that you get this one piece that makes it so you can put it into this thing called the citric acid cycle, the TCA cycle, which is well, anyway, there's lots of names for it called so we're going to get into that. So now, before we get there, I want to meet some of my players. Remember I said I'm going to tell you that there's going to be some things that when you hook them together, they're going to form they're going to form pieces on there. What time is it right now?
It's probably time for a break.
Let's do a break, and then we'll go on and do the rest of it. Yeah, let's do that.
So let's take a
Okay, somebody give me a better pointer that's much brighter, that if I point at something, I've got to get me one of these. Now, does DNA make these? I'm not sure. Probably not, but anyway, it's up. Okay, so I do want to spend just one moment talking about these players. And it's a big picture concept of what happens to these things, other than counting all these amino acids to get a final count. The big picture thing is that almost everything is going to have hook these things on. Hook it on to use it, hook it on to use it, and usually it's got the hooky part and it's got the active part. Okay, so let's go to these. So this right here is just a whole bunch of nucleotides. The ones on the top, I gotta make sure I get this one. The ones on the top up here were used by RNA. The ones down here are used by DNA. That makes the A, the G, actually this is RNA and this is DNA. This makes the A, the T, the A, the G, the T, the C. You remember in school you've learned A goes with T crosses and G goes with C, and they match together and they can form these codes. Okay, right here, so that's using it for, if it's using it for that, it's using it for this end, and then these phosphates are crossed right here, so cross, going across on this phosphate, and this one hooks to from another one, like this one will hook to this one. And so that it's using it for the shape of that. That's what it's using that for when it's using it in DNA, RNA. And this is an adenosine or adenodide with the adenosine. So whenever you hear about that, like adenosine or the A many times in the name of things, it's that guy with some stuff attached to it. Okay, so here I have here's my NAD to NADH. That's the one that I do the grab electrons. It's going to have this adenosine group with an extra phosphate, so it's like a diphosphate, and then it's got a special sugary group and an end here. Actually, this end over here is nicotinamide. It's actually what you get as part of vitamin B3. So if you're having vitamin B3, it allows you to make more of these NADs. And NADs are used to grab electrons. So it means your body doesn't have to make it if you get that. So that's why vitamins are important, because many times vitamins make the things that make things. Okay. Now, the FAD is kind of similar, where it's got this is an adenine, the same kind of the A from the nuclear base, but it's got this piece hanging out here. Then again, I'm going to use this all until this is where I gather electrons. Like up here, this is where I gather electrons. All of this stuff is to place it on the thing. So I have to have a slot for that little flatty thing there. I have to have a slot that'll hold those little two hooky ends. I have to have a place that can hold those charges, and it'll hold it in place so when it does something, it's up, and then I throw it off, and then I go off to the next thing. So it has to hold it on the protein. So almost every single protein that's going to have to connection with any one of these guys is got to have a shape on it for that. Plus, it needs to, if it's got an NA, if it's got to do the FAD, it's got to be a little further away from the active site because it's got a little longer string to put the thing that's going to do something, but it's going to have that shape in it. So that shape depends on what happens to it. So every one of these enzymes, or each one that does one of these, doing it with one of these things, it's got to have that shape on it. No matter how many curlicues, how many things, it has to somewhere have that shape on it. Okay. This is now your ATP. So this carries electrons, this carries electrons. Oh my gosh, that is basically this is your adenosine, and now they just showed this going inward. I don't know why they did it, but it moves around, that propellers around. But anyway, it's a flatty thing, and this right here is another place that it can hold things, and it's got 2 phosphates, and if I add an extra phosphate, I get adenosine diphosphate, ADP, adenosine triphosphate, ATP. Oh my gosh, energy coin. And that's going to fit. If you're going to try to take a phosphate off for phosphate, it's got to fit on there with all those little shapy things on it. Whew. Okay, so I want you to realize a lot of these enzymes have a lot of very similar places to put things. Okay, now I can go pretty fast. I just want to say the players that are in there. So, this is my CoA, which is going to hold my little 2-carbon group that I'm going to use. And guess what it has? Oh, it has an adenosine group. Yay! I'm Team Ribose. It's a ribo. And this has got that same group on it, except it has a little extra phosphate to crunch on a little bit, have an extra hooky place. It's got 2 charge places there, so it can hook it on there. And then it's got this long, stringy thing, which really you might have gotten from when it built it up from pantothenic acid, which is vitamin B5. Therefore, if you want to make more of these CoAs, this is one of the things you want to put in your diet. And most time you get it from, if you eat a balanced diet, you get it, so don't worry about it. Okay, now we're going to go to citric acid cycle. I'm going to go fast through here. I first want to show you ugly diagrams. I missed it. This shows this shows all the molecules it's making. It's changing. This shows all the players on the outside, fully done. Oh my gosh, it is so messy to look at, so hard to do. I like this one a little better. It says, okay, here's my cycle. Here are my enzymes. Boop, 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 boop. Here's the names of the things that goes in between. And this is the places that I'm going to have some special things in and out. Okay, so now I'm going to go fast. I have 10 things I'm going to go through here. I'm going to go through a lot of enzymes. And so I'm going to show you that they look kind of like, oh my gosh, they look kind of like this, all different shapes and different sizes. But in the end of the day, when I do some cataloging them, oh my gosh, I get 9 places I can have them, and actually less than 9 because some do double duty. But so we have a 430, a 780, a 366. Each one is the size of it. And I want you to realize it costs. The bigger it is, the more it costs to make. And so by the time you add up all the ones in that citric acid cycle, I'm going to get 3,931 ATPs amino acids I had to hook together to make those ones. And it's going to cost me about 7,800 ATPs, energy coins. It's going to cost. Okay, so let me go back down to the electron transport. I'll skip that. And this is a cartoon that doesn't show much. I like this cartoon better because it shows more. This is actually kind of the shape of these enzymes. And this is complex because this right here, this one has 45. In the humans, 45. In bacteria, it has 13. So, and we're going to see, what's the size difference between having 45 and 13? That's one of those kind of interesting things. And it has to have 45 put together, all in one place to work. And this one has a separate amino acids. This one's going to have a few, but this is roughly the shape of it. It goes through complex 1, complex 2, complex 3. It's only one protein, so we don't call it complex, so we don't give it a complex name. And complex 4, and this sometimes is called complex 5. That's the pump. These pump the protons by using the electrons that it's dumped and gets the protons down there to make an electrostatic potential, which shoves them through, which causes the pump to go, and that's going to be at the end. Okay, so let's, I can get rid of that one. So one of the things to show about this is on the first one, it's got to transfer electrons from way up here, down to 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 here. Each one of those is got to want the electron a little bit more, just a little bit more, just a little more, in order for it to go down. You start switching those, it won't work. Or it'll really super slow it down. And it has to do that every single time. And then a funny thing is you can kind of understand that everybody that I've ever seen on this particular molecule says, and it's got this sulfur group out here. out in the boonies. I have no idea what it's for. They'll always say, yeah, it's there, but I have no idea. Maybe structural stuff, I don't know. But this one's out there doing nothing. And we're talking about a lot of organisms have that one just sitting out there that we don't really know what it's doing. So basically, you're going to be pumping electrons in there. When you pump electrons in there, you're going to then, when you make the electrons flow down there, it's going to cause structural changes in this part right over here. Oops, I didn't mean to do it. Am I off my... Okay, it's going to actually, you can see this little band going across here. It's actually hooked together, so when you make this, it makes this, as the things go down, it makes that thing change each time it goes down. And when it does that, it kind of does this. And when it does that, it opens and closes things and pushes protons through. Yes. So it uses using electrical energy to do mechanical energy to make protons go up. Okay, all this shows right here, it's a lot of stuff right here. The red things are just binder proteins and to help it put it together, and says, if you were to put it together, this is what we find how it might be put together, blah, 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 blah. And again, I could spend more time on it. This is how you might put all those pieces together. I love this diagram. This diagram is telling it for a lot of proteins. See the gray area? That's bacteria. See the gray area? This is also human. It's the same size. That's where the core 14 are. Now, then all the rest of the 30 that are in human, that's the white ones, they're kind of like straps, kind of hold together. Now, if you're a plant, you don't need those straps because it's sitting in the middle of this bilayer, and it's only moving like this at lower temperature 70. Once you're at 100 degrees like us, and so these straps are probably there to keep it in place and keep things going so things happen the way it's supposed to happen. And you need that in higher temperatures, you need more things to help it. But in the end, what are we going to do with this? We're going to count, to make this thing, to make complex 1, you need 9,000 amino acids. How many? Is 9,000 a small number or big? That's a lot of amino acids you have to put together just to make this, to get one, to finally get all the things you're going to get from the glucose all the way down to make all the ATP. And if I get that process, in this one section, only one took 9,000. Holy, it is the biggest one here, so don't worry about it. And now the picture of it. And complex 2, it does another thing. And I don't have time to tell you the difference between complex 1 and complex 2. It's just it has a different source of electrons coming into it. So basically this complex 2 is 1,272. This is a low player in the numbers game. It doesn't cost that much to make this guy. And then we have this thing called, I just want to mention this because between complex 1 and complex 2, they both end at CoQ. And CoQ in humans has these 10, it has 10 sets of these things, so it's really long. In mice, it's CoQ9. It's a lower temperature. In a higher temperature, you need a longer thing to make sure it doesn't get out. And in yeast, it's CoQ6. Because it's really low temperature, it's not going to escape from that membrane in there. And I want you to realize that whenever it's doing all this electricity stuff, it's doing this stuff inside a membrane, insulator, to let all these nasty electrons be moving. All in this, so it's got an insulator. Ooh, I love it. So it knows how to do that to keep it all in there. This is cytochrome C, one protein. Okay, oh my gosh, only 104 units. That's the lowest one in this so far. It just got to hold a heme group. This is number 4, which does the very last thing, where it does the very last pass of electrons. So it has to go down a couple from some coppers to some hemes to then to water to go down to put them onto oxygen to make water. Okay, so what's the uptake here? For complex 4, it costs 1,900, and you have to. I'm trying to do it with the, actually I probably should hold 2 of these at the same time. That way I can do it with this. I don't touch that. Okay, so that's not that much. You'd think, it sounds like it's doing a lot of things, but there is a lot of things you have to add into it, so I'm not counting the cost of finding those things and adding those things. And so now if we get the total of the electron transport, electron transfer complex, it's going to be 14,928 amino acids of a total of, give or take, 30,000 ATPs it took to make that thing. So this is the big part, the accounting part. I want you to see how many things before you can get a single glucose through. Okay. Then the ATP complex, the only thing I want to mention here is that this thing is made of 20 genes. Those 20 genes, 18 of them are on the nucleus, 2 of them are actually in the mitochondria. And look how they're spread. There's gene 1, gene 2, gene 4, gene 7, gene 10, gene 11, gene 12, it's on, it's on the 14th chromosome, the 17th, the 18th, the 20th, the 21st. And it's got to gather from all these different, remember those single pieces of chromosome that's you, 23andMe? It's going to have to find them all over the place, bring them together to make this particular machine. You'd think they'd be in all one place. If I was a smart man, I'd put them all in one place. So it makes this machine. In this, the big takeoff here is that this machine will end up it'll take potential energy across here to drive the protons up here to create a mechanical energy that then forces these little things, the alpha beta things go around like this. Actually, they stay still, but the little pump thing goes again, hits it, and so it goes, and as that little thing, that little spiral thing in the middle goes, and this pair over here goes, each time it does it, makes an ATP, makes an ATP, makes an ATP, as the thing goes, so it takes potential energy to drive a mechanical energy, which makes a chemical energy bond. Oh my gosh, all these things happen at once. Of course, this happens naturally. It happens all the time, I'm sure. And we're talking about how many amino acids it needed. Now, this is the way it actually exists, is in a dimer. I only counted the monomer. And they think the reason it has a dimer there is because it's got a little fatty end on both sides, and that when the potential above gets too little, so it can't work right, it goes like this, and it plugs the opening. When they pump enough protons behind it, it opens up, and now it can start going. So it's really cool, and it's always found as dimers, and it always pinches the membrane. So it's a really cool thing. Anyway, so that actually is an electron micrograph. They actually can see that by it's so big you can actually see it. Okay, Grant, for complex 5, 6,733, and all the, now I didn't say how to put it together. It's, no, I'm not taking the energy of that. So that's a lot. So if I go now and I get to everything all together, to get the whole thing, I can take a glucose, go all the way down to then get everything out, just to make one. I had to have these factories in place. It had to take 31,833 amino acids, a couple variants in between there. Now that's human, so maybe bacteria might be able to get away with 25,000, maybe down to 20, I'm not sure. I haven't counted bacteria. Most of these are for human. And then it takes a whopping 63,000 ATP. Now, when I get to the end, I'm only getting around 28 out. So that's a lot of energy investment before you even get the first one. So one of my takeaways on this, is it natural? And I would say no. You have to put so much energy investment into it that the only way you can have this going is if you already started with it going, and then you can make a lot of, in fact, you usually need, it's one of the notes I have on here, well, first of all, how do you align all those, figure out the electron potentials to align all those electron transfer centers to make sure they all go from stepping down into who wants what more, and to get it in the right direction. 13 to 15. Before you can even use the pump, you got to pump enough H's down to make the pump. Okay, now, so I don't know how many glucose you take to first pump it up before you can start getting it out. And then you need membranes, you need where'd the code come from to make the proteins? We don't know. That's a big sticky. And how do you construct all these proteins so precisely? I didn't count how to do that. So it's a lot of cost. And I would have had a break there, but obviously I didn't make it. I'm going to skip the plant thing. The plant thing is just whatever I did here, do it in reverse. Okay. And use light to force it to go the other way. Okay, so where are we? We have all these marvelous reactions, and there are places you can change things, but there are some things you can't change in these things. Otherwise, it will not work. There are diseases where people have changes in it where it makes it so they don't work and they don't do well. So give about 31,000 amino acids, about 28. That means it would take about 2,000 glucoses before you can pay for all of that. Before you even get it going. So would that naturally occur? Probably not. It's just from that side. What about the supply side? Let's say you took all the life on Earth out and you tried to find, let's say glucose, or let's say amino acids. You took all the life out and you went into, like on the next planet over, and you tried to find amino acids, enough of them to do this kind of, I need to at least have 20,000 of them just to do this part, just to make the ATP so I can do all the other stuff. How many amino acids do you find there? Well, you might find a few here and there. And yes, because we can find a couple here and there doesn't mean that we have enough to actually put it together. And do we have the information to put it together? No, we kind of don't. So, so the answer is no. I don't think from the supply side it actually works on the physical end of it. And energetically, to make the peptide bond, it's higher in energy. Therefore, it's going to tend to want to go both ways, and it's going to break and make if you just add heat or use a general catalyst. If you use the DNA catalyst that makes it, the reader only makes it go one way. It makes it low, and it makes it only go one way, and it doesn't add any heat, so it doesn't have enough heat to go up this way, so it forces it to create it in such a way that it only reads it one way. The reaction only goes one way, even though it's energetically unfavorable. That's why you need ATP. So anyway, where does the information come from? And then I'll kind of probably stop with this one, because I have other slides after this, but it's not going to help in terms of this, is first of all, you start with DNA. We used to think DNA was simple, because all you do is you take DNA, you make a protein. Hello, how hard can that be? It ends up that we know that we actually take DNA to make a first version of the RNA, which we need to snip and slice and re-put together to make the kind of the final version that goes to the reader. You have to have this massive reader, which actually has 3 RNAs with about 30 proteins around it, all mixed together so everything can fit right, and plus these tRNAs. So now that gets a lot of level more complexity. Now, whenever you get that, finally make that protein on the string, you have to get something that folds the right way. Okay, there's another level of complexity that goes in with that. Then you have to have protein complexes. We're not just making individual ones. You have to put them together so they work together cooperatively and do all the right things. And then you have that also needs to be pieces in the right 3D order. We need to, and it also needs to fit all the reactants, the controls, the coenzymes, everything it needs to also fit in there, so that's another level of complexity. And then you have to have multi-cell specialization, which is built into all things that have multicellular organisms, like you. It even gets, so it ends up that this idea of the information and where does it come from, it gets more and more complex as we look at it further and further. And I think from the information side, I say it's very unlikely that we're going to find something out there in the physical world that is going to be able to produce the information needed to, they're trying, but that's the crux, and that's a big thing of evolution. I'll stop there. So, are there any questions that you may have?
Yes, if you have a question, please come forward and we'll form a line and